All right. So um let me just review my notes because I don't exactly remember what was happening. Okay, so there was a bunch of specifics, right? So we figured out that these could be our primers, except for the GC content was all out of whack, and so we couldn't do that. Um, let's go back to the other one. I believe it was primers in Gibson 2. And so here, did we determine basically, okay, so we had this. Okay, so we did again determine that if A and B are the primers, then the actual insert sequence needs to be B reverse complement, then the actual protein reading frame or whatever, and then A. So, and so why is that? That's because if we have, oh, this is a 3. This is the plasmid, right? That's the plasmid because, okay, yeah, we want these pictures. So, oh wait, no. Right. So this is what we end up with. We end up with, after the linearization and PCR, we get A is on one end and B is on the other, or BRC. So A, BRC. So that's actually right. So this is correct. So this is fine. So this gets chewed up. So what we want then is, yeah, BRC, G, and then this is going to be what? It's going to be A, because this, yeah, so this is going to be A. Okay, I understand this logic. So basically, let's open up that repo with the bio. And we should just be able to, so I don't know if I stored them. So we should probably store them. But if I just do UV run this, this seems right. Yeah, okay. So if we open up benchling and then we log, and I'd like to actually try their little assembly thing because they had a thing for it, but okay, so we were doing this section basically. And so what we're gonna do is instead of having this old LAC promoter where we need this cap binding site, we're just going to remove the whole LAC thing, and we're just going to put it. We're just gonna order the sequence with the promoter, the operator, because splicing it in here seems just genuinely dumb. It just doesn't seem like it's gonna work. So, all right. So I want to start writing up the exact protocol. Wait, actually, I should be able to do lab notebook. Get right to it. Okay. Okay. So this is going to be the assembly protocol. So the inputs are going to be that we have the puck 19 plasmid, and we also have and so if we go to twist bioscience, this thing, we're gonna have whatever the twist gene fragment, and so we need to figure out what we need to do with that. But so the first step is going to be the linearization of puck 19. So the first thing that I believe we're going to do is, oh, we don't do this, we do this, is we are going to I believe it's just add primers and, well, I guess we want to and determine the program based on GC primer length or whatever. And I don't know what the best order of operations is here. Like, we probably won't be able to do it all in one day. I actually want to try this again because I don't remember how this worked. But let's just let's make sure that okay. Okay. So what we've done is now we've okay, and then basically the difference here, we don't want a custom vector, but we want to select our vector, right? How to select vector. So we want puck 19, and I believe that we want puck 19 because there's licensing issues here. Yeah, so these things all products carry a research use only license for the end user. Research use covers any use of the plasmid for research purposes other than commercial. So, we don't really want to get into that game, but I think puck 19. Oh, really? Dude, what is that? What is that? What can I use for commercial use? I mean, not that I'm using it for commercial use, but So, and I guess the advantage, maybe we should look at some of these high copy as is the GenBank download. Let's look at the map. Cuz what I'm wondering, So yeah, dude, where did they put it in? That's, I guess, what I want to know. So is this going to come with annotations or not? Because if it doesn't come with annotations, what's the freaking point? Okay, so the clonal genes is significantly more expensive. Okay, so let's go back to benchling. And this is going to be the, what did they call it? P-amp high copy or something? Oh, we don't want this. P-twist amp. Okay, high copy. P-twist amp high copy M cherry. All right. And then what we want to do is we want to upload a GenBank. Well, can I just upload the zip file or no? I don't know how GenBank works. Okay, it seems like it worked. So does this have okay, great. So where did they insert? So this is the insert. I guess they didn't give me the name. That's dumb. They should have given me the name. What is that? Is that the Ori? Insert, what is this then? Okay, so they added overlapping. Okay, that backbone thing is kind of dumb, but that's fine. So the insert literally starts at 1. Is that right? Wow, that's pretty cool. I don't know why I think that's cool, but that's cool. This is the Ampar promoter. I feel like it's going the wrong way. I think that the exported GenBank just didn't get the direction right. Okay, but what I wanted to know, I guess, is, I mean, how did they do it? I kind of want to know. Like, can I read more about how they do this? I mean, yeah, I would like to know how they actually do it. One thing that I thought was interesting also is the economics of this. Like, my understanding is that Twist makes their own stuff and they don't sell it. They only sell the service, which is, interesting. But how do they do it? Do they say how they do it? Because I get that it's likely this phosphorimidite oligosynthesis, and then I don't know how they, I don't know if they use like I don't know how they assemble it though. High throughput silicon based platform miniaturizes the chemistry required for DNA synthesis. This drastically reduces the reaction volumes by a factor of 1,000,000, while increasing the throughput by a factor of 1,000. Clonal genes are made by cloning an insert into a vector. After synthesis and cloning, we use next generation sequencing to verify that the insert is 100% sequence perfect. The figure below showcases an example of an error-free clone. So we got to write down some of these numbers because this told me absolutely nothing. Okay, wait. Let's go through and just write down at least how much it costs. So okay. Okay, so it's 150 just default settings. I don't really know what other settings. So um yeah, okay, I guess I'm not going to be able to do that. All right, let's just do it based on subtotals and assume the shipping cost is the same then. All right, so the clonal gene, but the thing is that's not with Puck. Actually, oh wait, okay, I don't know. Is it based on base pair count or not? It probably is. I don't know. The pricing models here are so weird. It's like not clear what the hell they're doing. Okay, so if I change this to Puck 19, does the price change? What are these like restriction sites? I don't even know what. Oh, okay. Okay, so it's the same price. Okay, so the clonal gene is gonna be 150, and the gene fragment is going to be, and we're just talking about the without a promoter and without anything like that. Okay, so now let's do. Bro, I hate this thing. This thing is so dumb. Okay, this is probably it. Yeah, 7. Okay, so then, but the base price of the of M Cherry fragment is $50. So it's $100 cheaper to do this, but of course I have to buy all the reagents to actually do the assembly, but I don't really care about that. Okay, but the whole goal of this was to figure out what the format. Yeah, so what the format is. All right, so let's just do this. Oh wait, I'm not gonna be able to do this on stream. Oh, okay, but this is all I need. So the clonal gene, what is it? What does this mean? Like, what format are they gonna give me it? Is it just gonna be in water? I don't even understand what. Yeah, help me understand quantum physics. Um, when you order a clonal gene as opposed to a gene fragment, you're actually buying a plasmid clone containing your gene insert. Twist synthesizes your sequence, inserts it into one of their standard cloning backbones, then ships you DNA in a few purified plasmid DNA. Oh, yeah, because a glycerol stock is a cell stock. This is wrong, but that's okay. So, by default, it is shipped as a dry DNA pellet. Okay, all right. So clonal genes. Okay, wait. Is there a source? Lyophilized. Bro, where do they say lyophilized? I don't even know. I mean, it's actually, what's funny is like a really interesting aspect of all this is the logistics. Like finding methods like lyophilizing DNA so that it can be shipped at ambient temperature. Like that's a huge advancement. Okay, so all right, let's go through the flow of this is the clonal gene. So let's go to my orders, my drafts. And then let's go to the gene fragment without adapters. And it's important that we don't get the adapters. I don't know why would you even want those adapters? So if we continue, do we get the same question of whether or not we want the what the hell? In solution not available for 2mm tube. Okay, so I should expect it says fixed maximum amount per well, but does that mean that I actually get does that mean that I actually get 1,000 nanograms, or is that just the maximum? So for 2 milliliter tubes, you can only select dried down. You get a lyophilized pellet of DNA. If I choose normalization, gives you exactly. Yeah, that's what I'm saying, man. Okay, so let's just for safety say that we're gonna get uh for the fragment, we're gonna get 750 nanograms of DNA. Okay. Then okay, tell me how many copies of the gene 750 nanograms is if the gene is 710 or 11 base pairs. D- uh, and it's dsDNA. Okay, it'll do the math. It'll assume 50% GC, which is probably pretty close, right? Did we get that metric? I don't know. I trust all this math. Actually, I don't know if it used Python. Let's see. I mean, that's a lot of copies. You know, nanograms, when you're talking about DNA, nanograms is actually a lot. Okay, so this means for 711 base pairs, we have 9.77 E11 molecules. So okay, so I am planning on doing a protocol, a Gibson or a hi-fi assembly to insert my gene fragment into Puck 19. I'm wondering if I need to PCR the fragment or if this is enough. I also am about PCR to amplify so that if it doesn't work on the first try, I won't have to spend another $115. I guess that would probably be the best. So we just read this protocol. Interesting. Okay, so they have a lot of protocols here. All right, let's just read one. Oh, I hate this thing. I mean, why is this top thing so big? All right, let's just get the PDF. Yeah, that's better. Thaw the electrocompetent cells on ice. Transfer 50 microliters of electrocompetent cells to a pre-chilled electroporation cuvette. Okay. Use 1 microliter of the Wait, what? Oh, this must mean reaction, the master mix. Mix gently by pipetting. Once DNA is added to the cells, electroporation can be. Wait. This is the transformation protocol. This is stupid. This is not even what we want. Assembly reaction of a PCR fragment. Protocol for cloning repeat elements. Protocol for bridging with single-stranded oligo. Protocol for assembling annealed DNA. I think it's going to be just this one. Assembly reaction protocol. Guidelines for using it. PDF. Use this protocol for standard double-stranded DNA fragments with varied overlaps. If you're using fragment sizes smaller, we would recommend you using a... Okay, that's fine. Yeah, okay, so that seems cool. Okay, so we have this, now we need to learn. Do we amplify the fragment? And how to resuspend. Okay. NEB recommends a total of okay. So you don't have to PCR amplify a twist gene fragment to use it in NEB Builder Gibson if the fragment already includes the overlaps. And B, you have enough mass. Many people assemble directly from the dried down fragment. That says there are good reasons to PCR once and bank material. Yeah, see, that's what I'm thinking, bro. Is like, okay, what NEB and Twist recommend? Yep, design the, okay, so I have that. Well, we will have that. Bro, I love that like literally every single time, dude. There's a different one. Nebraska Educational Broadcasting. Like, I don't know how they're coming up with this, but it's hilarious. Yeah, like I just don't know why that's so wrong. And it's been wrong. I don't know, whatever. All right, DNA amounts. For one insert into a vector recommends yes. And we saw that in the thing with the insert 2 times the vector molar amount. Concrete recipe. Um. Oh wow. You know what? That's actually kind of crazy to think about because um. Okay, like here, let's just draw out my understanding of the protocol. So let's do a new one. This. Wait, let's actually rename this thing. This is going to be the assembly protocol, basically. And then we can just go into Zen mode. What is it? Control dot. Nice. Okay. Okay, so we're going to start with the Puck 19 plasmid and the lyophilized fragment M cherry. Now, the idea here is oh wait, actually this is going to be in cells. So what we actually need to do is erase all this. So we need to do mini prep plasmid purification. And then what happens here is now we're going to get pure Puck 19 circular. Okay, then what we have to do after that, though, is we need to PCR, inverse PCR to linearize. So now we're going to get that like A, G, B, R, C thing. Okay. And then, so at this stage, this should be, if we expect a similar yield to the P glow, then this should be, I think it was 100 nanograms per microliter. Okay, so this is what we have so far. So we're gonna keep reading and add to this because we want to know the because I don't know what the concentration should be after this. But so this is what we have so far, and then we need to figure out what we want to do with the fragment and go from there. I don't want to use the lower end. I feel like I want to use probably the higher end because it should increase the chances that it works, right? Okay, so at 20 nanograms ish. Yeah, okay, so the 750 nanograms is like what we're ordering. So PCR versus no PCR. NEB manuals often say to PCR amplify fragments with a high fidelity polymerase prior to assembly. This is generic advice to ensure clean ends. Don't know about that. And to add overlaps, tails as needed. It's not mandatory if your synthetic fragment already has the right overlaps. Twist specifics. Twist gene fragment guidelines discuss fragment cloning. If you ordered adapter on fragments, note the universal adapter. If you ordered adapter off, you provide the overlaps yourself by fragment design or by PCR partners. Okay. When I would skip PCR. Your fragment sequence already includes the exact overlaps. Okay, they do. And you have ample mass. I also do. You want to avoid but okay, but I think maybe because we need to figure out then how much, because maybe I could just like take half, right? Can I take half? Gel purification. I've actually really wanted to do that. That would be pretty sweet. Um, what is the clean ends thing? Oh. But I'm gonna have to order those primers anyways. Yeah, so I'm gonna do adapters off, but okay, but half of the 750 nanograms or something, and then PCR it and save it for later. How much do I need to do PCR? Oh wow. Okay, wait. So gene uh all right, Twist ships its DNA dried down or resuspended. Then shipping for the should be cheaper, man. I wonder if they've done experiments. You know, they just say this, but like there's got to be a okay. For resuspension, briefly centrifuge the tube or plate before opening and resuspend a nuclease free tris EDTA buffer. Okay, so it's basically, so this is like, what did they say, 10 millimolar tris TE buffer? Oh, they didn't even say the concentration of, just TE buffer. pH of 8. Is there a good YouTube video of making TE buffer? Look at that spatula, man. Okay. All right. So I don't know if I have to make it or not, but like, can you just order it? Oh, let me do this really quick. You might not be able to. Bro, TE buffer is cheap, man. Bro, TE buffer is cheap, man. Okay, well, that's good to know. I didn't know that. Some of these chemicals are expensive, some are not. So this stuff is like cheap. So that's good. I'm actually really happy about that. Some of this stuff is not cheap. All right. So I just buy it, man. I wouldn't even fucking make it. Okay. So we literally just like if we have 750 nanograms and we want to make it a concentration, they recommend at least the aliquot should be at least 10 nanograms per microliter. Yeah. Yeah, that makes sense. Um Okay, so then once we have a liquid stock of this, okay, so let's figure this out. So the resuspension guideline is so the twist recommendation is to resuspend the pellet, the lyophilized pellet, to in 8 pH TE buffer with a minimum concentration of DNA of 10 nanograms per microliter. So if I then aliquot. So if I do this, I can still PCR even if the DNA is in TE, right? It doesn't say anything about the sterility of this. Does it say it on the bottle? I mean, I'd at least prefer the one that where they say that it's sterile, because otherwise, who knows? Who knows? All right. Yes, you can PCR from DNA that's resuspended in TE buffer. Here's what matters. PCR tolerance of TE. Tris doesn't interfere with PCR at the small amounts you add. The EDTA is the only potential concern since it chelates magnesium ions. Twist uses very low EDTA. The resuspension guideline is what? $100? Also, wait, how do I store the Resuspended DNA is stable. Okay, so I'm gonna write that down. So resuspended DNA stable for 24 months at -20 per twist in TE. Okay. Okay, so what did it say? Oh yeah. Bruh. What the hell? That's silly, man. I know. Why is this so slow? That's stupid. I'm not gonna change how I use. But it's so slow. It's so slow that I gotta go on mobile to read the responses. Did it load finally? Let's just say it's 1 kb. The vector is 2.8 kb, and the vector DNA mass. Well, I have. Wait, the vector DNA mass. I should be able to get. Because what did we do? I think I made. Um. I think I made 75 microliters of 100, which is 7,500 nanograms. So this is like the total amount of Puck 19 I should expect. So I don't know. If I write 7,500, what is it going to give me? Wait, don't we want more? Well, I didn't actually get what the positive control thing is. What is that? So what we want is okay, let me think about this. So we're trying to figure out a number of things. We're trying to figure out, first off, we don't know the resulting concentration from. Okay, so let's just write down what we know. Okay, so we know that the I have a strain and glycerol stock of E. coli expressing PUC19. I plan to mini prep to extract. In the past, I believe I got about 100 nanograms per microliter of and 75 microliters of extract. 7,500 nanograms total. But I will use this too. So we also need to, once we linearize it though, I think we need to do this DPNI digest thing. It is slow though. I don't know. Does anyone else feel that? It's so slow. Something is wrong, dude. So I'm sort of thinking like maybe we want like 1 picomole of vector and 2 picomoles. One nanogram, dude? That's hilariously small. That's a lot of DNA. A microgram of DNA is a ton. Even a nanogram is a lot. Is that right? Okay. And then I think that's right. Let me just do it on paper. So let's say we have 50 nanograms of 700 base pair thing. So the molecular weight. So first we're gonna do 1e minus 9 grams for 1 nanogram. Then now we have grams of the fragment. Now we want to multiply by 650 grams per mole times 700 BP. So this will expand to be 600. This times 1e minus 9. Oh, yeah, I got this wrong. Then we are going to divide by 650 grams for 1 mole per base pair. $650 grams for 1 mole per base pair. Okay, so then we just need to divide again by 700 base pairs. So what is this 1e minus 3 thing, though? Okay. So if we have, okay, so that's the grams per mole. So now if we have nanograms, we multiply it by 1e minus 9. Okay, then don't we just, why is the 1e minus 3 here though? I think it should just be divided by. That's what I thought, man. That doesn't seem right at all. So then the other way, if we have moles, what's the best? What's the? I've never seen units in Python ever. Is it just like SymPy or something? I don't even know. Wait, why is this? Oh, it's a picomole. Wait, this is to mole. Nanogram to mole. Okay. I've never heard of this. This is crazy. Right. Do we have anything? I think we need to multiply this. Oh, wow. That's how you use this? This is insane. Oh, yeah. Okay, good. Okay. I'll add those two. All right, so we should be able to now do something. Okay, so if I have... Okay, so now what are we doing? We're trying to figure out... I want... Okay, what do I have? I have a solution that's 100 nanograms per microliter of the Puck 19. And we will... So, okay, so we're trying to figure out how many microliters. So we have... we have 75... Okay, so we want picomoles to nanograms. Okay, so p mole to ng. Oh wait. Yeah, 1, and then we have like 2,800. Okay, so this is 1820 nanograms DNA that we need. Oh wait, didn't it? No, it recommended yeah, that seemed high. It recommended something less than that. Oh, point one picomoles. So 182 nanograms. You're right. Okay, so um um uh for hi-fi, we want we want yeah, like zero point zero 0.03 to 0.2 picomole of the fragments and a ratio of vector to insert of 1 to 2. We pick 0.1 mole of vector and 0.2 mole of insert. Or wait, picomole. Okay, so we have so puck len puck 19 is it actually that? Okay, so then we want nanogram puck 19 is going to be 0.1 times that. Yes, that's correct. Can I run this though? Okay, cool. At least I can run that. And what is that number? Okay, so this is a 182 nanograms. So the in the past I have gotten about 100 nanogram per microliter, 75 microliters of concentration plasmid P glow from mini prep. Extrapolate to assume same yield for puck 19. Okay, so we need 1.82 microliters. So this is in microliters of, but actually that's not right because the above is wrong because we need to linearize. Well, we need to linearize first, and PCR will make it extremely, or will make it, because it was saying it start with like 1 nanogram. Any for Q5, NEB recommends, what is it? 0.1. Oh wait, what is the actual recommendation? We need to figure that out. Okay. Bro, it's like ordering this stuff is crazy, man. Ordering this stuff is freaking crazy. All right, PCR. Here we go. Let's just read this. We got a PCR protocol. And the biggest freaking head bar that you could ever imagine, man. Takes up like 40% of the page. Come on. I think I'm gonna make some food. But what is that reaction buffer? What is that? I'm just gonna use the master mix, dude. I don't give a frick. Okay. All right. So in that case, we don't need this and we don't need that. Oh, can I change this? Oh, it's like a real spreadsheet. That's kind of fun. Wait, so what are we trying to figure out though? We're trying to figure out what the concentration is going to be after the. So if we do it like this, I don't like that it says that this can be the template DNA can be variable. So I don't know why the concentration of the template DNA is just like, yeah, throw whatever you want in there. Like maybe it doesn't matter because it saturates. Oh wow, that's faster. I think the other one said 1 minute per KB. Wait, really? I didn't see that. Oh, So if we're adding, let's say 5 nanograms, okay, so even if we say we have 5 nanograms, then we would need, so we need a dilute. Okay. What the fuck? Right. Okay. Um. So if we have what do I do? What do I dilute? Um, okay. So it's going to be um so here I wish I had a better selection tool, but let's see if I can. Yeah. We're not even ready to talk about this yet. Okay, so what we need to do is we need to. Oh no, it's raining. Maybe it won't rain too bad. Um. Okay, so in this step we also have to dilute it. So we need to dilute 1 to 100. Um. So that, and then we add like 1 nanogram of plasmid to the um PCR mixtures. And then how do we predict so how do we compute how much linear plasmid we will have directly after the PCR linearization if we assume we okay, you know what? I'm gonna go inside. Gotta end this.